You are looking at the distribution of grades after an exam. You are in a German grading scheme, you create some bars and add them in, and then you see, well, this kind of looks like a Gaussian, perfect grading, what I was expecting. You fix the standard deviation or variance because you're a fair teacher, so that the spread is always similar, but where is the mean? Where is the mode of the distribution? You could use a maximum likelihood estimate, of course, but then you see there are outliers, and the maximum likelihood estimate is not robust enough. Can you encode prior knowledge? And indeed you can. In this video we will derive the posterior and maximum a posteriori estimate. Hi, welcome to this new video. As said in the intro, we will derive the posterior and the maximum a posteriori estimate for the univariate Gaussian or normal distribution, and I will use these names interchangeably. In the intro I said we fix the sigma and the mu is unknown. Let us encode this in a directed graphical model. So we have the directed graphical model as follows. The essential ingredient is of course the data that we observe. So let's create an observed node that I will call xi, which is the grade of the ith student. We have n students, and the grade of the students is affected by two parameters, and the first one is a deterministic parameter, which is our sigma, or you can also call it sigma squared, the standard deviation or the variance. That is what the teacher fixed because he wanted to expect a certain spread of the distribution of grades. He has an unknown mu, so let's make it a latent node, and this unknown mu depends on parameters that we will add in shortly. So now we have a dataset. The dataset is the grades that the teacher observed or that the teacher graded, and they are given as, for instance, 2.2 and then a 1.7 and then a 2.7 and so on and so forth. And in total there are n grades that the teacher gave, and this is of course mapped to our n students, and that fits our directed graphical model. Right now we know that our grades are distributed according to a normal. That is our hypothesis here, but we still don't know what the distribution or the prior distribution of the mu is. So let us look at the likelihood again, which we would use for a maximum likelihood estimate. And the likelihood is given over the dataset under the latent mu and the deterministic, well, let's call it sigma squared, under the deterministic variance, and under the assumption of IID, so identical and independently distributed data. We can just take the product from I0 to capital N-1 over the probability of xi given mu and under the parameter sigma squared. And of course we know that this is nothing else than the normal distribution, so we expect a normal over xi given mu and with the parameter sigma squared. And if we plug in the functional form for the normal, then we get the product from I0 to capital N-1 over 1 over sigma times square root of 2 pi, then times the exponential, and in the exponential we have minus 1 over 2 sigma squared times xi minus mu in brackets squared and then closing brackets for the exponential. And if we apply the product to these two terms, then we first apply it to the constant here, and it is multiplied n times with itself, so we raise it to the power of n, and we have 1 over sigma times square root of 2 pi in brackets raised to the n. And then the exponential, we multiply this term n times with itself, and then we see we can add up the exponents, and this is just a constant factor in front of the summation, and we have minus 1 over 2 sigma squared times the summation from I0 to capital N-1 over xi minus mu in brackets squared. And here we see that our likelihood, and the likelihood in essence was nothing else than the conditional of the data that we observe given the latent mu, is a function where mu appears in the exponent squared. So let's note this down. Mu appears in exponential squared. I think you get what I mean. So there's a square in here. Of course, there's also the negative sign, which is quite important. And then there is the exponential. And this is our motivation to use a Gaussian or normal distribution as a prior of mu. So then we have two normal distributions. We have our actual normal distribution over the grades and our prior normal distribution over the mu. So we say use normal or Gaussian as prior. And we can also confirm on this because we will then figure out that the normal and the Gaussian is indeed the conjugate prior, because we will then have a posterior which is also a normal distribution, which is a handy property of normal distributions. Okay, so let's complete our directed graphical model here and add the hyperparameters, or the parameters of our latent mu. And they are first a so-called mu0 and a sigma 0, and also you can square it, either it's standard deviation or variance. And now don't be confused. If I have no index, then I mean it is a random variable, mu. And if I have an index here, so a mu0 and a sigma 0, I encode hyperparameters and they are fixed. So this is the prior knowledge. And let's note this down, this is the prior knowledge. And with the help of this prior knowledge, the teacher can encode where he expects the mu to be, and he also can give a standard deviation of where he expects the mu to be. This is not a standard deviation that he is expecting for the crate distribution, it's just a standard deviation he's expecting for the prior over mu. But we will see about this in a second. Okay, then let's put this in, and we have mu is distributed according to a normal over mu under the parameters mu0 and sigma 0 squared. And our xi is distributed according to a normal over xi with a latent mu and a deterministic sigma squared, so the standard deviation a teacher was expecting. Based on the directed graphical model, we can use the properties of factorization to create the joint distribution. So let's call this the joint distribution. And the joint distribution is the probability density function over mu and our x vector. And recall, x vector is just the collection of the n crates. We want to fix this to be observed as the dataset. So we say the probability density of mu and the crates of the n students are the crates that we observe. This will then be, according to the factorization, the probability of mu times the probability of the x vector being the dataset under the latent mu. In shorthand notation, we also call this p of mu and the dataset. Then let's plug in what we have. So here we have again the p of mu, and under our IID assumption that we also used for the likelihood, we can just use the product from I0 to capital N-1 over p of xi is the ith crate observation under the latent mu. And if we then plug in the distributions that we're expecting, so the distributions that we modeled here, then we have p of mu is the normal distribution over mu under the deterministic parameters mu0 and sigma 0 squared. And then we multiply this with the product from I0 to capital N-1 over the normal over capital Xi being the observation Xi under the latent mu and given the deterministic and fixed parameter of the standard deviation sigma squared. Well, then let's plug in what we have. For this, we will get a 1 over sigma 0 square root of 2 pi exponential minus 1 over sigma 0 squared times mu minus mu0 in brackets squared. And for this, we will already use what we had up here where we looked at the likelihood. So we got the 1 over sigma times square root of 2 pi in brackets raised to the power of n times the exponential of minus 1 over 2 sigma squared times the summation from I0 to capital N-1 over the ith crate observation minus mu in brackets squared and then closing brackets for the exponential. Then let us apply some exponential calculating rules and add the two exponents together because we are multiplying two exponentials of the same basis. That is the Eulerian basis. And then we get 1 over sigma 0 times square root of 2 pi, then times 1 over sigma times square root of 2 pi raised to the power of n times the exponential of minus 1 over, well, of course we should have 2 sigma 0 squared of mu minus mu0 in brackets squared minus 1 over 2 sigma squared, then the summation from I0 to capital N-1 over xi minus mu in brackets squared, and then closing brackets for the exponential. And this is our joint distribution for the directed graphical model. Now let us look at the posterior, and let us derive the posterior by the help of Bayes' rule. We know the posterior that we want to get is a mu given a dataset. So we want to have a probability of mu's given the observations of grades that we did. And by applying Bayes' rule, we are getting, this is the fraction of P of D given mu, recall that was the likelihood, times P of mu, which is the prior, divided by P of D, which is the marginal. And we don't want to calculate the marginal, so we are just working in terms of the proportional. And so we say this is the proportional to P of D given mu times P of mu. And then we see, well, this is nothing else than the factorized joint, so that is P of mu and D. And essentially this is what we just calculated here. And then we see a general result that appears quite often when we use Bayes' rule, is that the conditional is proportional to the joint. And we use a similar strategy to the derivations of posteriors that we've done in previous videos, that we will use portionals over proportionals to then in the end find a functional form of a potential probability density function that we know, and then we can just add the normalization constant again, which simplifies our life by quite a bit, because then we don't have to take care for the marginals and all the other normalization constants. Then we see that the posterior is proportional to, well, let's just copy this for once. So we have 1 over sigma 0 times square root of 2 pi times 1 over sigma times square root of 2 pi in brackets raised to the power of n times the exponential of minus 1 over 2 sigma 0 squared, then mu minus mu 0 in brackets squared, minus 1 over 2 sigma squared, then the summation from I0 to capital N minus 1 over the squared differences from the mean. Then we can again work in terms of the proportional and ignore these two normalization constants here, and we are getting the exponential term. And let us already evaluate the square by applying binomial's formula. And we are having minus 1 over 2 sigma 0 squared. And then for this one, we are having mu squared minus 2 mu mu 0 plus mu 0 squared. And then minus 1 over 2 sigma squared of the summation from I0 to capital N minus 1 over xi squared minus 2xi mu plus mu squared, closing brackets. And then let's apply the summation to each of the three terms individually and multiply all of them with their corresponding coefficient. So this is now equal, and by this I mean that is equal to this line, but of course it's still proportional to the posterior, right? So we have the exponential over minus mu squared over 2 sigma 0 squared plus mu mu 0 over sigma 0 squared minus mu 0 squared over 2 sigma 0 squared minus 1 over 2 sigma squared times the summation from I0 to capital N minus 1 over xi squared plus mu over sigma squared, the 2 and the 2 cancels, times the summation from I0 to capital N minus 1 over xi. And then lastly, we have minus mu squared over 2 sigma squared, and we would have the summation from I0 to capital N minus 1 over this entire term. And since there is no I or index I involved, we can just multiply with n, because we would add this up n times. Then let's look at the exponentials and collect all the terms with equal degrees in the polynomial of mu. So this means we have here a term in mu squared, and here we have another term in mu squared. Then we have a term in mu, which is here and here, and we have a term that does not contain any mu. These are these terms. Of course, take care again. Now I'm only speaking in terms of mu, which was our random variable, and not in terms of mu 0, which is just a parameter, or in more precise terms, a hyperparameter, which is fixed up front. So you could also think of it as an A, a B, a C, or whatever kind of parameter name you can think of. So after rearranging, we are getting the exponentials, and first off minus mu squared over 2 sigma 0 squared minus mu squared over 2 sigma squared n. For the term in mu, we are getting plus mu 0 over sigma 0 squared. And here we have plus mu over sigma squared times the summation from I0 to capital N minus 1 over xi. And then lastly, we have these terms here, minus mu 0 squared over 2 sigma 0 squared minus 1 over 2 sigma squared, and the summation from I0 to capital N minus 1 over the xi squared. And then the closing brackets for the exponential. And we could now apply exponential rules, since we have in essence an addition or a subtraction of these terms here. So this would be e to this times e to this times e to this. But we can also just say it is e to this times e to this. And in these terms, we would then get a constant in front of the exponential. And then we could again work in terms of the proportional. So we will delete these, or not delete them, but ignore them and work in terms of the proportional. And then we are getting the exponential of only the yellow and the orange terms. And we can simplify them to bring them together by the help of cross multiplication. And this means we multiply mu squared with sigma squared and mu squared with sigma 0 squared. So we have mu squared, sigma squared, and then plus mu squared sigma 0 squared over 2 sigma 0 squared sigma squared. And I put the minus of these two in front of the fraction so that the minus applies to the two terms in here. And let's do the same for the term which is only linear in mu. And then we would be getting mu 0 sigma squared plus mu sigma 0 squared times the summation from I0 to capital N minus 1 over xi. And we divide this by sigma 0 squared, sigma squared, closing brackets for the exponential. And we have to add an n here because this was missing in our multiplication. For the further simplifications, let us move all the terms in mu after the fraction. So this will be going here. And the same is for the terms in mu that are just linear. They will be going here. And we can also factor out the common denominator. So we will move this one in front of it with the help of a bracket. And in order to do so, we have to multiply the second term by 2. So we are getting the exponential of minus 1 over 2 sigma 0 squared, and then opening brackets sigma squared plus n sigma 0 squared multiplied with mu squared. And here we are having plus 2 times, and this was the multiplication of the 2 because then it would cancel and we would get this term again of mu 0 sigma squared plus sigma 0 squared. And here we have the summation from I0 to capital N minus 1 over xi. And then we multiply this with a mu. And then we have the closing brackets for this multiplication and the big closing bracket for the exponential. And the reason I did this is that we can now see that we have a quadratic equation here in our exponential. And if we note this as an a and this as a b, hypothetically we would have here a plus 0, which we could note as the c. Then our exponential can be written in terms of the exponential of minus 1 over 2 sigma 0 squared, and then we have the a, b, c, and we have mu squared plus a b mu plus a c, closing brackets and then closing brackets again. And we use this format of a quadratic equation in order to bring this into standard form, which is given as the exponential of minus 1 over 2 sigma 0 squared of opening brackets a times in brackets mu minus d squared plus an e, and then closing brackets for this one and for the exponential. And the process of going from this form to this form is called completing or completion of the square. And we will use the general results that I derived in an earlier video. For this we have that a is a and d is given as minus b over 2a, and e is given as c minus b squared over 4a. And we see a is a, we don't have to do anything here. And for the d we have the minus and b up here, and I forgot that it has to be negative because we put out the minus in front of it, so that minus and minus is plus again. And if we then plug in the b as we defined it, then we have minus 2 sigma squared mu 0 plus sigma 0 squared, and the summation from I0 to capital N minus 1 over the great observations, and we divide it by 2 times, and a was given as this one here, which was sigma squared plus n sigma 0 squared, and we see the 2 and the 2 cancels, and the minus cancels too, so we have a plus here. Then let's plug in the e, and for the e we have, well, c was 0, minus, and then this term squared, so we have minus 2 times sigma squared mu 0 plus sigma 0 squared times the summation from I0 to capital N minus 1 over the great observations xi, then closing brackets, and then another closing brackets for the square, and we divide it by 4 times sigma squared plus n sigma 0 squared, and we see the minus squared will be a plus, so we can cancel this, and the 2 squared will be a 4, so this cancels with 4, but there is nothing that would cancel with the minus, so we keep the minus in front of the e. And by this, we then get p of mu given the data as the exponential of minus 1 over 2 sigma 0 squared sigma squared times, and then we first have the a, and the a was given as sigma squared plus n sigma 0 squared, and then we multiply it with mu minus the d, which is this one here, is sigma squared mu 0 plus sigma 0 squared summation from I0 to capital N minus 1 over the xi's divided by sigma squared plus n sigma 0 squared, closing brackets, and then the square. And then we have the e term, which is minus the fraction of sigma squared plus mu 0 plus sigma 0 squared, and then the summation from I0 to capital N minus 1 over xi, and then we divide by sigma squared plus n sigma 0 squared. And of course this should be proportional because we're not equal yet, it's missing the normalization. And here we can make a similar argument to before. This is just a constant because we have the multiplication with this factor here, and then we have e to this minus e to this, or times e to this, and this will just be a constant again, so we can work in terms of the proportional, or we proportionalize again, and we get the exponential, and I just write this down one more time. So we have minus, and then we can multiply this back in, and we have sigma squared plus n sigma 0 squared over 2 sigma 0 squared sigma squared times mu minus, and this lengthy term, which is sigma squared mu 0 plus sigma 0 squared, the summation from I0 to capital N minus 1 over xi, divided by sigma squared plus n sigma 0 squared, and then closing brackets squared, and then closing brackets for the exponential. And I hope that it is now clear what I meant by we do a couple of proportionals and then we reach at a functional form which looks like something that we've known before, or that we know. And here you could say, isn't it just another normal? And that's true. So because it has the same form, it has the exponential of a minus, then something in front, times mu, which is the random variable we are taking the probability density function over, minus the mean in brackets squared. So this will be the mean of the posterior normal, and here we will find the standard deviation or variance of our posterior normal. So here we have a mu n, and by n I indicate the parameters of the posterior. And here we can decode our variance or standard deviation according to, we know that minus 1 over 2 sigma n squared has to be, so I forgot the minus, maybe let's put this inside of the circle, and then we have minus sigma squared plus n sigma 0 squared over 2 sigma 0 squared sigma squared. And then we see, well, the minus and the minus cancel, the 2 and the 2 cancel, and we see if we take the reciproc and if we take the square, then we have sigma n is the square root of sigma 0 squared over sigma squared plus n sigma 0 squared. Now that we have all the parameters of our posterior, so our mu n and our sigma n, we can also derive the normalization constant, which was 1 over sigma n times 2 pi, and we would just plug in whatever we have here, and then we have our full probability density function. So we have p of mu given the data as a normal distribution over mu with the parameters mu n and sigma n and potentially squared, however you want to parameterize it. Let us note down mu n and sigma n for completion, and we have mu n was given as sigma squared mu 0 plus sigma 0 squared, the summation from I0 to capital N minus 1 over xi over the summation of sigma squared plus n sigma 0 squared, and that is the parameter of our posterior. Let us look at it a little bit in detail. If we break out the summation in the numerator, we are getting, this is equal to sigma squared over sigma squared plus n sigma 0 squared times mu 0 plus sigma 0 squared over sigma squared plus n sigma 0 squared. And if you recall, so let me put this here, the maximum likelihood estimate we derived in an earlier video was 1 over n times the summation from I0 to capital N minus 1 over xi. If we would multiply with an n, we would get the maximum likelihood estimate here. So this is similar to n times mu maximum likelihood estimate. What I want to show by this is that it is some sort of a weighted average of the mu 0, which was the prior knowledge or the mean or the position where the teacher expected the mode of the distribution, and the MLE, which he would use like naively if he didn't have any outliers and it's just like the first guess. So we are kind of augmenting the maximum likelihood estimate with our prior knowledge. So let's put this down. We have a linear combination, or you could also call it a weighted average. So this is a weighted average of MLE and prior knowledge. And with this in mind, I hope it also makes sense that the posterior is some sort of regularizing the maximum likelihood estimate. And we can do the same thing for the sigma n. And the sigma n was given according to sigma 0 times sigma over the square root of sigma squared plus n sigma 0 squared. And that is our result. And we can also rearrange this a little bit. And if we take the inverse again and square it, then we have 1 over sigma n squared is, well, sigma squared plus n sigma 0 squared over sigma 0 squared sigma squared, and we can break out the summation here too, and then we would have sigma squared over sigma 0 squared sigma squared plus n sigma 0 squared over sigma 0 squared sigma squared, a lot of sigmas here, and then we have the sigma and the sigma cancels, and the sigma 0 squared and the sigma 0 squared cancels too, and we have 1 over sigma 0 squared plus n over sigma squared. And here you can see that the sigma of our posterior is some sort of like the harmonic mean of the sigma 0 of our prior distribution on the mu, and the sigma, which was the standard deviation that the teacher fixed. So it is something like the harmonic mean. That's cool, right? With this derivation in mind, we now have information on the posterior distribution, but we also wanted to figure out the maximum a posteriori estimate. So what is the map? And we know the maximum a posteriori estimate is nothing else than the mode of the posterior. So the mode of the posterior, and recall the mode is the position at which the probability density function takes its maximum. And since we have a normal distribution here, we know where this normal distribution takes its maximum. And it takes its maximum at mu n, at the mean of the Gaussian distribution. So we can conclude that mu map is mu n So the mean of the posterior distribution over mu, and this was given sigma squared mu 0 plus sigma 0 squared times the summation from I0 to capital N minus 1 over xi divided by sigma squared plus n sigma 0 squared. And with this, we also found the maximum a posteriori estimate, and you could make the same argument with the weighted average as we did here for the mu. Finally, let us look at an example with TensorFlow Probability. For this, we first have to create a dataset, so we define a true mu and a true sigma of the distribution of crates, from which we then can create a distribution or like a sample of crates. And I will call this mu true. And let's say, for instance, the distribution is centered around 2.5, which is the average crate in Germany. And we have a sigma true of 0.7, standard deviation of 0.7. And then let's create a crate random variable, which is a normal distribution with a location according to the mu and a scale according to the sigma. And we can look at it and see it's a normal, no bed shape, no event shape, fantastic. And we can create a data set when we sample this random variable, for instance, 100 times. Then we can look at the data set and we see there are crates 1.8, 3.1 and so on and so forth. Let's first calculate a maximum likelihood estimate. For this we will use TensorFlow, then reduce mean of the data set, and we get a maximum likelihood estimate 2.43, which is quite close to the 2.5 from which the data set was created. Now let's calculate our maximum a posteriori estimate. For this we first have to fix the sigma. And the sigma fix, so this is what the teacher expects, because he just knows that he always creates with a standard deviation. So the standard deviation is then surely the same as we used for creating the dataset. Then we need a mu 0. This is where the teacher expects the mean of the distribution. And he says, for instance, oh, it's 2.3. I know it. And then it is sigma 0, where he encodes his uncertainty about his knowledge. And let's say, for instance, he is, well, not too certain, but so certain, like 0.2 standard deviation around 2.3. Recall that this is associated with the prior. And then we can translate the formula for mu n. And for this, we have first the sigma fix raised to the power of 2 multiplied with the mu 0. Then we add the sigma 0, raise it to the power of 2, multiply it with the summation over the dataset. So let's put this in here, close, close, and then we divide by, and the denominator was the sigma fix, which is just the sigma pure without any indices, if you recall from the derivation. Then take it to the power of 2, and we add, well, n was 100 because we took 100 samples, and multiply it with sigma 0, raise it to the power of 2. And that's our mu n, and we can look at it. And we know it is also our mu maximum a posteriori estimate, because that is equal to the mode of the distribution. Here you see, well, it's different from the maximum likelihood estimate. And by different, I mean it is even a little worse, so it's not as close as we are to this. But this is, of course, because we have this prior knowledge which shifted us more towards the 2.3. And if the teacher would have been more certain about it, then it would have been even closer to the 2.3. And soon we will see why this is useful. First, let us calculate the sigma n, so the standard deviation of the posterior distribution. And the formula was sigma 0 times sigma fix divided by the square root, so tf math dot square root of sigma fix raised to the power of 2 plus the sample size, which was 100, times sigma 0 raised to the power of 2. And then we can calculate it and see the posterior standard deviation is 0.06, so it's quite a sharp distribution around the posterior mode, which is 2.41. So let's also create the posterior over the mu, and for this we will use another normal distribution, and the location is with the mu n or mu map, because they are identical, and the scale, of course, is sigma n. Then let's close this, and here we can query, for instance, the mode of this distribution, and we see the mode is identical with the map or the mu_n, and for this we also show that the mode of the posterior is, of course, the maximum A posteriori estimate. But now there is still a question, why do we need a map at all if it is worse than the original MLE? And for this we will create a corrupt dataset, and corrupt datasets are really common in machine learning because usually you don't have perfect data, either it's noisy or your preprocessing is not as good as you want it to be. So let's create a corrupt dataset. For this I will copy the dataset into the NumPy world in order to change it. And for instance, in this case, the first 70 students hacked into the system and reduced their grades by 1 grade. So now we also have grades that are better than 1.0, but that does not greatly matter. And we can look at the corrupt dataset and see that the first are way better than we would expect. We even have negative grades, but it's just due to the way we sampled. And now let us create a new corrupt MLE. So mu MLE corrupt. And for this we again use tf reduce mean over the corrupt dataset. And if we look at the corrupt MLE, we see it's at 1.72. So that's far off from the 2.5, which our original distribution was. Because 2.5 is still the underlying correct value, but we can't just infer it anymore with a maximum likelihood estimate. Then let's do a mu_n or a mu_map, for which we put in the corrupt dataset. So I just copied the formula and I will call this mu_map corrupt. And if we then look at the map estimate, then we see it's a bad estimate, but it's closer to the 2.5 because we had the prior knowledge which regularized our MLE. And we saw that the map was nothing else than the linear combination of the MLE and the prior mode, and for this we are a little more on the safe side when we have corrupt datasets, which are really common, therefore always think of regularization. That's the end of the video. If you enjoyed it, I would really appreciate if you like and subscribe. There is more awesome content coming soon. Here you will now see similar videos, and I hope to see you next time.